So as I'm Glenn Shaw, there's two of us standing up here, and just to give a little background on John, he's taking the restoration seminar and needs to give, is it next week you give each student gives a 5-minute presentation?
So one of our students already is presenting.
And so he's just going to do the 5-minute spiel on his project, and that's what I'm going to be doing. I'm going to be presenting the work of two of my graduate students. One is John, and that's going to be the first case study. And then the second is Evan Norman, who's sitting in the back of the room, and they're different types of groundwater restoration or stream restoration projects. Now my background, as Robert introduced, I'm more of a mountain hydrology, mountain groundwater. I focus on groundwater, surface water interactions, lakes, rivers, if they're around, and I'm trying to use those as a guide to study groundwater. I have a lot of experience with isotopes and tracer hydrology. And a lot of what we're doing, it seems to be we're going to be focusing more on groundwater flow modeling. And I wish I could come up here and present like all the answers. I'm new to the restoration world, but the last few projects that have fallen into my lap and students that I've dealt with, I'd say the last 4, including these 2, have not just been groundwater, surface water in mountain systems, but have related to restoration of streams and how groundwater is important. And the title might be a little bit misleading because I'm not just going to focus on groundwater and surface water interactions, but the groundwater system as a whole in relation to stream restoration. One of the things, first of all, why understand groundwater for a stream restoration project? The first and possibly most obvious, and those of you who have been attending the seminars are familiar with this already, groundwater and surface water often behave as one system, especially the groundwater that's near surface water bodies. And that particular groundwater, we want to keep or enhance that connection when we do reconstruct rivers, and we need to consider it. And I'm not saying it's not considered in stream restoration. So any one of you out there who is a stream restoration person, I'm sure you've looked at groundwater in those studies. So the first case study we're going to look at is the Middle Fork John Day River in Central Oregon. And we're going to focus on the potential for drying up an existing wetland. And that became the major focus of the study. There were lots of questions. That Interfluve is a consulting company just in Oregon, or?
They have an office in Bozeman, Minnesota, and Maine, so they're throughout the country.
Okay, and they provided John with this project, and John got this on his own and came to me and asked if I would help advise. And then the second is that some stream restoration efforts focus on using surface water to enhance late season flow and groundwater storage. And so this case study is going to focus on Beaver Mimicry, which I believe 2 or 3 restoration seminars this semester have already brought it up. And I have to shout out to Evan in the back of the room. He worked for CFWEP, and he's just beginning his master's program, but he has 1, possibly 2 years of data already from his connection with CFWEP and the connection that CFWEP has with Great West Engineering that provided and asked for some groundwater monitoring. That's Amy Chadwick over there, and she's more of a ecologist, wildlife ecologist, and she got in touch with us and CFWEP for the groundwater part. And so with that, I am going to turn the time over to John to introduce his site, and then I'll go over some of the data.
Cool, thanks Glenn. Yeah, so I'm just going to give you kind of overview of the site and my project, and then Glenn will go into more of the technical aspects, such as the field work and some of the results we've seen. So is this on the pointer?
Yeah.
So as Glenn said, we're in Oregon, we're in Grant County by the town of Galena. If you haven't heard of it, it's because there's 9 to 18 people that live there throughout the year. So really small town, pretty empty area. There's not a whole lot going out there.
Totally redneck there. It's like white settlement road, you know?
Yeah, it's definitely out in the boonies, hard to get to, so it kind of added to the interest of the project, getting there as opposed to like Evan's sites are right up on the hill here. So, so before we go over like the site itself, I kind of want to talk about why are they doing restoration here. And first off is beauty. So they placer mined the area for about 60 years, starting in 1840. And so you can see these, we call them tailings, but they're really just waste rock. There's no contaminant, there's no heavy metals. They pretty much picked up cobbles and gravels, got the fines out, got their gold, dumped all this stuff. And so we'll show you the extent of that in a couple more slides, but they're ugly, nothing really grows on them. In addition to that, they moved the river channel, and I'll show you some images of that, and they made it a straight channel. So it used to be a meandering river with finer sediment, and now it's pretty much straight channel coarse sediment. And so that's actually pretty poor habitat for a lot of species. In addition to that, it kind of ruined a lot of recreation area. You can't really fish there anymore. There's really tight regulations, and there's a lot of dangerous metals in the tailings, so they want to get them out. But probably the most important aspect is for the salmon and the trout. And so the Freshwater Trust is a group that's a nonprofit that gives money to restoration in Oregon. And so they focus on salmon habitat. And so a really cool thing about the John Day River system is it's the third longest undammed river system in the lower 48, which when you think about that, is pretty remarkable. And when we're talking about protecting a species like salmon, dams are really important in that. And if we have a system that's not dammed, we really got to protect those because that's some of our best habitat for salmon. And additionally, the trout there don't do well. This is a small trout I caught, and that's about the biggest you can catch there. And it really just comes down to habitat because
so the one trout that was there, he caught. So.
Yeah. But it just comes down to habitat because you have a straight channel that's coarse material. Fish cannot spawn in that. It's poor habitat for that, so they've saw numbers go down quite a bit. So they've actually done work on the Middle Fork. This is about 8 miles upstream of where I'm working. And so this is after mining. Straight channel. This picture doesn't have it, but the whole area here was all tailings that they moved to the side. And just think of cobbles, boulders, no vegetation. And so what they do is they actually re-meander the channel. They put log jams, stuff like that into trap sediment, and you're basically remaking all that habitat again. And so that's what they want to do at my site. But at my site, there's some complicated things, and that's this wetlands here. So the river's over here, the Middle Fork, and it flows towards us to the north. And they have this wetlands directly to the west of it. And so the big worry is, if you re-meander that river, what's going to happen to the wetlands? Because we don't know if the wetlands were there before or after the mining. So they want to make sure they maintain those wetlands because it's a great habitat for a lot of species. Additionally, and I'll show you here in a second, there's a creek that is pretty much from where I took this picture behind me. And this creek, as you'll see, branches off and was moved by the miners, and they want to move it back to its original position, but part of that creek feeds the wetlands. So the big question is the wetlands going to dry up if you move that creek and re-meander that river? So this kind of gets into my goals, and I kind of see it as like my big scale goals and my micro goals. And so my big scale goals are just show, hey, putting groundwater models and stuff like that in stream restoration, it's really important to consider that stuff. And I want to show that you can implement these groundwater ideas into an actual stream restoration plan. And that ties directly into my micro goals, which is I kind of wanted to directly aid a project so I could see the results, actually do something. So this is just a brief geology. So if anyone's familiar with the area, we get the Columbia River floodplain basalts. And so this is the very extent of those. And all that really matters for what we're talking about is underneath our site is basalt, and it's pretty competent. So that's going to kind of serve as the bottom of our model, which Glenn will talk about. Other than that, we have just alluvium, so just river deposits at the site. So here's an overview of the site. And so you can see the tailings here in red pretty much cover the entire extent. You can see the Middle Fork, which is flowing up in this picture, is a straight channel. There's no meander to it. You have any of that habitat. wetlands are here, and this white is pretty much their fullest extent during the wet season. And then here's a really important part, Bear Creek, and you can see there's multiple channels. This one here actually doesn't connect to the river until another 2 miles upstream because it was moved by the miners on the other side of the tailings. And then this channel we'll talk about in a second is really important to the project. So I just zoomed in on Bear Creek. Middle Fork's over here, flowing north. Wetlands are here. Before they did any work, channel F was not here. So it'd come down from the mountains, one branch would go this way, and the miners moved it next to their cabin as a water source because they didn't want to walk down to E to get their water. And then the other branches go up and E goes off and eventually hits the Middle Fork. So what they've done now, and this happened this summer, is they got rid of channel B, got rid of channel E, and created channel F. So it essentially just flows out and straight into the Middle Fork as it should. And that basically makes a stream that wasn't connected to the river reconnected for salmon habitat. The big worry is, what is that going to do for this? Because this was definitely an input of water. And so now Glenn's going to go into more of the work we've done and results we've seen.
Yeah, so let me just clarify right now the overall kind of tools that we want to use in addition to regular, and I'll show you the monitoring that John has done. I went out to the site last month with him, and it was really good to go see that. And I'd never been to the site until then. But a lot of what John hopes to do is create a groundwater flow model, a numerical simulation that will more accurately represent and allow us to make predictions on how these changes and how the proposed changes as they reclaim the tailings and increase sinuosity in the stream, what kind of impact both of those, taking this out and increasing sinuosity and releveling the floodplain, will have on these wetlands. We don't have those answers yet, but we have wells installed and some field data, and we're currently, John's writing a report that's kind of doing a basic assessment of the hydrogeology of the area pre-modeling and what kind of flows we might have and what kind of observations we see in water levels and stream flows. So I'll be highlighting some of those. I'm going to give you a little baby lesson on groundwater flow. First of all, the reason we want to go into a more complex numerical model, and we first have to do the more basic Darcy's Law calculations. Now that we're going to do Darcy's Law, I want to talk about how sometimes it neglects, it simplifies. This is very simple math, and it simplifies and takes away some of the heterogeneity that might be involved in the system. And that can result in invalid results. Also, on small scales especially, this can produce dramatic variability between the simplified version and a more realistic version. And so we don't want these unanticipated kind of changes. We want to be able to see what a well-calibrated model might say in addition to a basic hydrogeologic interpretation. So Henry Darcy is the father of groundwater, and he ended up coming up with this equation. And it's very similar to heat flow, electrical flow, stuff like Coulomb's law and stuff like that. But basically what I'm going to walk you through is John's field instrumentation and monitoring and how it's used to solve for the flow of groundwater, which is Q. And I'm going to show you how different things he did to solve for this parameter K, which is the hydraulic conductivity. It's how easily does water flow through the subsurface. And A is the area, cross-sectional area that groundwater is flowing through. And then this DHDL is a gradient, and it's basically the slope of the water table. And so John ends up going and putting in, I think the next slide shows, this is the network of wells that he put in. We talked about it quite a bit before he went out to the site. And he went there almost every week this summer while he was working in Western Washington. So he'd finish his work in Western Washington. He would drive out to the site. He would install wells. and he would monitor the water levels and install pressure transducers that would continually record water levels in most of these wells and staff gauges. The yellow dots here that say MW are monitoring wells, and the red dots here that say SG are staff gauges. In the tailings there's a bunch of pools, and we assumed or wanted to know, watch their response and see how well connected, if they represent groundwater levels. And we put in monitoring wells near, this is really flat little old oxbow, I assume, and then these are steep hills that come right down to where it gets greener. And so as you can see, kind of dotted the network with areas where we could monitor the water levels. And then he put some up near the creek, staff gauges, and over where the Bear Creek is. Okay, advance. There's a monitoring well. They were hand augered or dug with a post hole digger. That happens to have a SC meter measuring it. And those are the staff gauges that John made to install. And then all of these have been surveyed in. I think you had a slide in your last presentation of that. So we can get actual elevations of water levels. Not sure if you can read this very well, but our wells are only maybe 5 feet deep. And so we don't know the thickness of the alluvium, and we don't have budget for drilling and geophysical surveys or anything like that to see. So John looked at wells in the near vicinity, and this is distance. These are about 3/4 of a mile away and up to 4 miles away. And what I want to highlight is basically we can see that a 20 to 40 foot aquifer thickness is probably reasonable. And we may actually test model sensitivity to the two depths to see how different our results might be. And bringing you back to Darcy's law, this has helped in aiding our area of groundwater flow. This is another thing that John did. It was his idea. It was kind of cool. And he thrashed his hands. When we were out at the site, we went from the south end to the north end, and was it every 15 feet, 20 feet? 20. Every 20 feet, he took a steel rod and he pushed it into the ground, because the top layer is capped by a kind of a fine sandy silt. And then you get into gravels. And I need to clarify that the wells, the hand augering, we could go down to the gravel, but we couldn't really penetrate the gravel very much, or he couldn't. I'm sure I wouldn't be able to. And so here's a picture of him. I have a video of him sitting there pushing it down, and he could feel when he actually hit the gravels and even cobbles. So the wells are in connection with the gravels and cobbles, and so we think they reflect actual groundwater levels, but they're really actually completed right at the gravel silt interface. For hydraulic conductivity, I brought a little show and tell. Normally we would go in and we would take something like this slug, really simple sand-filled PVC pipe, and we drop it down a well, and we watch the water level response, and we put a pressure transducer in there, we record every half second or second, and we would see how fast and what rate the water levels come back down to static water table. And that gives us an idea of how easily water flows through the aquifer. And we couldn't fit them in 1 inch, in 1 inch wells, so John added water to the well, and to increase hydraulic head and watch it go back down. And since those wells might be reflecting more of the silt that they're placed in, John took samples of the gravel. He reached down, dug down to the gravels, and he sieve tested the gravel aquifer material, and using a thing called like Hazen's Law, I think is what they use, where you can take the distribution of sediment and you can make a calculation on what the hydraulic conductivity would be. And so the wetland silts, using a kind of a high and low estimate, seem to be less than 0.1 feet per day. The sandy silt more like 0.5 to 1.5 feet per day. And then the gravelly sand with cobbles that he sampled, these were with slug tests, And this is with sieve analyses seem to range between 10 and 100 feet per day. And those are reasonable results, and he'll use those to help calibrate his model. Here's surface water hydrograph that's at the USGS gauge for the Middle Fork John Day, and then these are stream flows that he took with time every time he was out there at Bear Creek. And the scales are different, but the curve, snowmelt pulse, and then going after snowmelt to kind of the low flow period of time. Just so we have an idea of what the surface water level, surface flows are. And river stage, right? Okay, river stage could be important for modeling. So this is busy, and the only thing I want to say is this is all the wells and staff gauges where we had continuously recording pressure transducers. And you can see he installed most of these on May 10th, a few of them after. But you can see for the most part, most of these see a snowmelt pulse where the water table rises up during snowmelt and then continually declines through the summer. And maybe in September, October, when the weather, climate starts, rain and other things, you get some increases in water levels. I'm going to zoom in on a few of these. The first one is right there, MW3. I have to get oriented. So you see the snowmelt pulse, but you notice during the dry season it stays, these are relative changes in head. So these are not put into actual elevations in feet above sea level yet. But you notice that it has the lowest relative drop, and it seems to have this constant source of water. These other wells kind of dried up over time, but this one seems to be receiving what we think is a constant source of water, and that's going to complicate the model because we don't know what that flux is. But the flux on the boundary of the model that's coming in, it seems to be pretty steady through the dry season. The next one is, this is MW6. It's at the south end of the wetlands, and you can see, now I got it backwards, MW6 actually, as you go from snowmelt on, the wetland actually does change in size, right? And as it's drying up, you actually see that this well gradually dries up. MW8 is right where that old channel of Bear Creek came and connected with the wetland, and then it was removed sometime. That's this line right here that I'm following. And we know that they went and removed that branch of the creek sometime in July, and John's pretty sure that right there, that it was July 29th. Have you confirmed with them?
Yeah.
Okay, so you can see immediately after they took that small tributary away and made all the water flow through the main Bear Creek channel, you can see a decline in water levels. And then MW9 is up on the hill where the main channel is, and you can see a decline from snowmelt. But it seems to a little after the 29th, but you see a bit quicker of a response with increasing hydraulic head. So we're not sure about that, but it seems to be that way. And then staff gauge 9 is the only monitored pool that stayed completely saturated, and that is this. And it seems we are arguing that there's a constant source of water flowing, coming from up gradient, and that water is kind of moving in this general direction. This is actually, we're going to highlight, actually it's right here, MW8 and MW9. And this is after they removed the creek that flowed by MW8. And it's the relative change in hydraulic head after the creek. So we zeroed out at the time they removed that creek. And you can see that more water was flowing, more volumetric water flow was flowing nearer to MW9. And you see MW9 constantly has a higher head. And there's pretty big decline, a foot, more than a foot of MW8. So clearly that we think that creek removal is lowering or causing some decrease in the water table that might be. This is just for, we team up with Robert Powell a lot. We meet with him almost every week and talk about our restoration sites. And we broke up these sites when we were there. John actually did it into zones, and we use these 1 meter square plots to try to sample and identify the different vegetation types in hopes that that might qualitatively help us with our understanding our groundwater flow model. But that's yet to be determined. I think you guys have met. And then nearing the end of this part of the presentation, the groundwater flow model. John's getting a water balance made using Darcy's calculations and getting all the pieces that he needs to create first a steady state model and then hopefully a transient model that will simulate and mimic the changes in water levels that we see, and then we hope to make some predictions on how does rerouting Bear Creek impact the wetland. And so we have to come up with a way of adding a wetland to our groundwater flow model. We've already bounced some ideas. How will future changes to the Middle Fork impact the wetland? So we hope we can add some increased sinuosity to the creek and add that into the model and see if it keeps the wetlands wet or not. And is the wetland primarily fed by surface water or groundwater? We hope to answer that ourselves. This is just taken from Aquavea's website. That's an example groundwater flow model. That's not our site, but he'll have something like that where these colors represent different water levels through a system. And with that, I'm going to pause right now and I'm going to ask people if they have maybe a few questions on this before we get to the next site. You can wait till the end too if you want.
Is the the elevation of the wetland significantly higher than the main channel, or are they about the same?
So if you go back to the site image with the, or even just that one, just any one of the full thing.
This one?
Yeah, so I see that.
Yeah.
So pretty much it's a pretty smooth, like I guess you'd say, water table slope down to the river, because the river is gaining throughout the site. But there's no, like, are you talking about like kind of mounding kind
I'm
of
just curious of the relative position of the wetland to the channel.
Yeah.
How much higher is it?
Oh, this is probably about 3 feet from the channel in terms of elevation of water.
Okay. Cool. Good question. John LaFave always asks good questions. All right, I'm going to move on to Evan's project, and of course, running out of time and not giving it justice, but we'll walk through what we can, because this is new to me. A couple years ago, Amy Chadwick approached Andy Bopes, who's working on his PhD at MSU, and Andy's down by Lima in that general vicinity doing beaver mimicry studies with Robert Payne. And I'm on his committee, and she had somehow heard that and approached Andy, wondering if some of these nearby sites on Basin and Blacktail Creek in the Butte Highlands, if he was interested in monitoring or if he knew anyone. And he got me in contact with her. And I was overwhelmed with other projects, but I was intrigued, and I like working with Andy, and I thought this was a good way to form a connection with him. And so I went out and visited the sites in 2016 prior to river restoration, or to the installing these beaver mimicry structures. And Amy was hoping that I could find a student or a group of students to help monitor. And in 2017, I did find one student who began a master's project, but he found other things to do after a summer of monitoring. But Evan was working at CFWEP at the time, and Great West and CFWEP, the Clark Fork Watershed Education Program here on campus, have a connection, or had a connection. I'm not sure where that is now. I assume there's still a connection. But Evan would go out and monitor some of these water levels. And Amy did a lot of the well installation herself. She did the restoration, she guided that, and I just piggybacked onto it a little bit. And I would say that it was the beginning of this year, thanks to Amy, she kept feeding us papers. And that was when I first started really reading papers on natural beaver dams and what kind of impacts they have on the ecosystem and the hydrology. And then I started looking at papers on beaver mimicry structures, and there doesn't seem to be a lot on beaver mimicry structures, and it interested me, and I made time to really, with pretty much no budget, focus my efforts on this. And you know, Amy's been really good at providing equipment needed and stuff like that through Great West. But let's talk about some of these overviews of beaver mimicries, and not just on Blacktail and Basin, but why use these beaver mimicry structures. They are little structures that kind of imitate what a beaver would do by damming up water or restricting flow. There, question?
I happen to live out there, up in the Highlands. I live at 60 Moose Creek Road. I might have talked to you maybe a year or two ago. You guys go up Limekill, and I go straight to Moose Creek there where the road V's and Roosevelt Drive goes. I live about a mile down the road there.
Okay.
I have a pond there, and I wanted you guys to I have some ideas and stuff, and I wanted to get a crew of kids out there or something and talk about it.
Oh, we should.
I dug the pond a little deeper this summer. I wanted to do it this summer. I wanted to get a hold of guys, but my dam broke. And I got muskrats in there instead of beavers, and because I had some cattails in there, and they ended up getting demolished. And this guy says, "Well, you don't have a healthy pond unless you got healthy cattails." And I was looking at him, and I had this gal look up on her phone. I'm computer illiterate and stuff. And she looked up muskrats, and they happen to eat cattails. So,
okay.
What does it relation? I mean, there's a lot of stuff.
Evan, is this one of the sites we're currently monitoring? Is this up the highest site?
I don't believe so.
Well, yeah, you guys were going up the other way. I don't know if it was last year or the year before. I was trying to get you guys to go around and take a look at it, because I seen you guys going up Limekill, and I hollered at you guys.
Okay.
I used to work up here at Tech and stuff and that. And then last year, I was down at the Hyper, and they were having a symposium and stuff. And I think somebody called me, but I wasn't sure from up here. But my dam had broke, and I was kind of like bummed about it, because, you know, I want to make I would put solar panels up. I got a well right down by where the pond is.
Well, maybe we can talk after the seminar, and no, it's okay. We can talk after and just find out where you're at and what's going on. Oh, I'm gonna trip. No, it's all right. Public seminar. So, yeah, that we always want ideas. But yeah, so some of the things we look at, or that have been noted from either natural beaver dams and maybe not as much from beaver mimicry structures, is first of all decreasing sediment loads of incised streams. Without the dams, the streams cut down, they incise, they don't get to meander and spread out as much as they used to, and so we want to decrease that and create kind of a riffle pull environment. There are some studies I've read about decreased nutrient loads, phosphorus and nitrogen. We're not really looking at that. A lot of the same studies actually do say that with caution. They talk about increased organic carbon fluxes as the nitrogen and phosphorus decrease. There's some ideas about decreased surface water temperatures, and and the first thing we think of is, well, you're pooling water on the surface. There's more solar energy. It could warm water. Well, it's whether or not you bring back willows and other things that might shade the river a little better. And so I'll show you a little data from that. Maybe enhanced evapotranspiration. We don't know a lot about that. Andy Bopst has done some numerical models, theoretical models that look a little more into that. And we are using some of his ideas from his models as a guide for what we should be looking at. With pooled water and increased vegetation, we think these were going to produce a better natural habitat for a variety of species, probably macroinvertebrates, fish, amphibians, mammals, birds, you name it, probably gonna help in the long run. And then in bold are some of the reasons that Amy approached us, and Amy approached is kind of this, do we reconnect the river to the floodplain? Well, that wasn't her main intention, because you can see that actually happening in some of these scenarios. But it's kind of a what's going on with groundwater and surface water storage during late season flows. Can we store water and release it so there's higher flows during the low flow period months, July, August, maybe September? And then there's some talk about whether you get lower overall flows, whether less flashy surface water, what happens to groundwater flows pre and post restoration. And we don't know all these answers, and like I said, some of Andy's numerical models that are theoretical have helped answer some of this. But I'll save that for a seminar that Andy gives. These are what the Beaver mimicry structures look like. Our sites, there's pretty much little lodgepole pine stumps put into the river bottom, interwoven by willows and other vegetation, maybe some mud, cobbles, stuff like that. And as far as the sediment, I don't have pictures of it, but you can see after one season of having these on site, you can see sediment building up behind these mimicry structures. So they really is to me, it's impressive to see these incised streams filling up with sediment the way they're supposed to. Here's a figure that shows that this is a couple of the sites on Blacktail Creek. This is kind of up a little higher in elevation, and this is lower. This is the site that I'm going to talk about the most in this presentation. And this is a site where all up and down through here there's been some restoration and several of these mimicry structures installed. How many there, Evan? 20?
Students yet.
Yeah. And then this is over, and these green dots are piezometers, little monitoring wells, and the blue dots around here are surface flow monitoring sites where we have 3 seasons of data, really. These wells and monitoring sites are here as a control. We wanted to monitor where there hasn't been restoration and compare it in a very similar environment where there has been restoration. And then I'm going to maybe have time for a couple slides on Blacktail Creek, and there's a couple sites that where a control and a restored site, control, restored site, and I might show a little data from this site. Just last month monitored, and we have a little bit of data from just 2 weeks after restoration occurred and seeing some interesting things. So in Blacktail Creek, again, the same figure blown up a little bit. This is the main area, maybe show a little bit of the control, but over in the restored site you can see there's a line of wells. There's a line of wells kind of going in this direction because we anticipate groundwater flow moving in that general direction, and we pretty much know that groundwater is flowing along the floodplain in that direction. We have some wells coming up onto this little bench, so we come up not too high, maybe 5 or 6 feet, and there's a few wells up on the bench, and there's a little line over here of wells where you start in the floodplain and move up into the bench. And these are steep slopes, and it's a bowl, and when you're down there it's a bowl, and then this is kind of a meadow-ish area, a bench, pretty flat, it's dipping towards the river, and then the floodplain is this narrow region here. And so here's a picture of surveying in. I think that's Amy. I stole this picture from Evan. These guys fed me all the data. Like these guys own the projects, and I'm just trying to guide them along. And but here's a staff gauge in the channel, and here's a series of wells. I don't know if you can see that. There's a monitoring well right there, and it's hard to see, but there's a whole line of them. Little wells, 3 feet, 5 feet into the ground. Here's a picture of us. I took my hydrogeology field camp to this site, and we did several tasks. And one of them, we went and added a few deeper wells, maybe 6 to 8 feet deep. A couple of those near some shallow wells for understanding the upward and downward movement of groundwater. And that is Evan right there, hacksawing and making slots. And there's, as he put it in the borehole, he's surrounding the screen with sand there, and then later a little bentonite to keep surface water from coming into the well. As I got excited about this, I approached Mohammed Khalil, who's in geophysical engineering, and he does electrical methods. And I asked him if he could help out. And he, without saying a lot, like Mohammed needs to explain this, but I'm just going to share the very basics. Mohammed had our geology and geophysics field camp come up and put a line here. These are 200 meters, so like 600 plus feet he would measure along here, he would measure along here, the two sides of the wetlands. It was in May, it was too wet to do the monitoring in the floodplain. He did a line across the road here, and he did a line across the road here, so we could, and what he's trying to do is, we couldn't it was too wet, water table was too high to map out the water table, but we're trying to map out the subsurface geology, and he can go about 120 feet, we'll say. And I'll show there's the students that are surveying in all the points. He puts this line out, puts electrodes in the ground, excites the electrodes, induces an electrical current, and depending on whether it's sand or silt or clay, the resistivity is going to behave differently. And here's a figure the geology field camp gave me. And without getting into too much of this, basically what we see is as you come up from the slopes, you have very shallow depth of soil to bedrock. That should be expected. As you come out onto, it's one of these, I think it's this line right here. As you come out onto the bench that's a little flatter, he estimated somewhere around the order of 60, 70 feet down to bedrock. So I was placing bets with the students. They were all saying, oh, 15 feet, oh, 20 feet. I'm like, I bet it's deeper. And then they all said it would be 30, 40 feet to bedrock in the floodplain. And he went down about 110 feet, and we never got to bedrock. So there must be some sort of fracture system going on, which is maybe why that river is there, cutting down and eroding the fractured bedrock. And so we'd love to have seismic or something up there to see how deep those fractures go. But we want to know how thick that aquifer is. This is a method called surface potential, SP, self-potential, sorry, I got it wrong. And he has this big cable that he induces a current, and he can, I don't remember if he goes from positive to negative or negative to positive, but he can detect upward or downward movement of water. He can detect basically the flow of water. And one of the cool things, kind of hydrogeologists always talk about the heterogeneity of the soil. Well, we didn't see tons of it in the actual alluvium. We see sandy, silty stuff, and resistivity shows that. But over on this side channel, over on this bench, we expect water to mostly be flowing in the direction of flow, and a lot of flow is probably going to be going from the high to the floodplain. But there must, there might be, I'm not going to say must, but this is a low zone, and they interpreted that to be basically a paleo channel somewhere a little deeper, where the floodplain might have been further out in that bench. Not sure how long ago in geologic history, but not too long ago. And there might be some water flowing underneath this bench and probably wraps back around. And just thought that was kind of cool to highlight what geophysics can do and show. With surface water flows, there's John. This is our hydro field camp. We went out and we did a bunch of surface water flows in August. Evan's been out there targeting a few sites, and we did a bunch of sites trying to do a surface water balance where he injects a high concentration of saline water and then a student measures the salt go through. It's like a pulse of salt, and records that, and you can calculate that into a flow. And every site we did that, we compared with a traditional velocity area method. Came out pretty close, and acceptably close. I don't remember the error, but we trust our surface water flows. Hydraulic conductivity. Evan went out with part of the hydro field camp and did water slugs, and also did Hazen's law from sieve tests. And basically from the sieve analyses, we have about 0.1 to 1 foot per day, so pretty low hydraulic conductivity, and that reflects the material we saw, that's silty, sandy material. And then 0.8 to 2 feet per day using slug tests analyses. So this seems reasonable, and we're running out of time. How about if we say, when we installed deeper wells, we calculated more of an upward gradient of flow. So most of the water's moving with the river, but there's a slight upward. We have some ideas on the placement of where we put these wells relative to the beaver structures, and we think that the beaver structures might be causing some upwelling, and that we're actually over on that end of the restoration sites. But we want to put in more sites and check that. Gaining or losing, we did a surface water balance. Those are sometimes tricky to tell if a site is gaining or losing, but in general we think it's a losing system down at the restored site, possibly because things are pooled up and the surface water is flowing into the groundwater. And it's more hazy up higher on the control where there hasn't been restoration, but we think there might be gaining. But next time we give a talk and we have more data, that could change. Radon, I have to do isotope tracers at least a little bit. We sampled some radon, and what this means is these are really low radon activity. Groundwater comes in contact with radon and builds up with radon. If there was groundwater flowing to the creek, you would have much higher, maybe not much, but in that granitic system, you would expect much higher, a couple hundred even. And so that supports the losing reach that we're talking about. With stream flows, here's cutting to the chase. The red line is the restored site. The other lines are non-restored. The red line is much more damped and much less flashy during high flow events, rain and snowmelt events. So the beaver structures seem to be preventing water from peaking up really high and then going down really fast. And if you look at cumulative discharge with time, going from August of 17 to September 18, the lines of the control are much steeper during snowmelt, much shallower, lower flows during the dry season. But the restored sites show higher flows rates, I would assume, and much more gentle during snowmelt, where we attribute this to possibly surface water filling up the aquifer and surface water storing at the same time. 3 slides that all show, I'm going to blast through these since we're basically out of time. 3 slides showing that pre-restoration in basically July and October of 16, pre-restoration, water levels go up in a well right next to the river. We don't know what's causing that or why 17 and 18 are different, but even over on the bench, further away from restoration, we see increase in water levels during high and low flows. And then we kind of see a similar pattern. Not sure what's causing the depression and the difference in 18 and 17, but we see differences in water levels. Temperatures, since restoration, we see that the temperatures are higher. And we expect that actually now. Pooled water, more sunlight, less willows shading. We hope when willows and other vegetation come in that ultimately we'll see a cooling of water. But 20 years from now or something. And Basin Creek that was restored, without getting into too much, Evan gave me this cool figure that says, okay, first of all, I don't have the same shot of the creek, but this site was dry. They restored it. They put like 40 structures. There's a lot of pooling of water. You could step across the stream like that and you'd have to jump pretty far to get across it. That's 2 weeks after restoration. 2 weeks after. And you can see the water levels relative to pre-restoration, post-restoration water levels with distance from the stream. We can see 2 weeks water in the surface has pulled up. It's slowly filling up the aquifer, but we anticipate with time these water levels further away, they're probably already high. We like that because Andy Bopes tells us that with his models that you want high enough hydraulic conductivity that you can fill an aquifer. But you want low enough hydraulic conductivity that when the flashy periods go away, the water is still stored and it slowly releases in July and August. And so we're hoping we're in the right soil types. And that's really it. Future, we're probably going to, a lot of available data, we're probably going to do some models. Evan, I think this is going modeling, and he's taking modeling next semester. And then probably want to take my hydro field camp to some other sites and do some of the similar studies. And I'll leave it at that. Any questions with going a little over?